Hello, welcome to my channel. In this video I'm gonna derive the circuit response equations of the series RLC circuit in frequency domain. In my previous circuit analysis video I derived the equation uh, for the series source free RLC circuit in time domain. I derived the equations of this same source free RLC circuit in time domain, where I solved differential equations and got the answer. Now I'm gonna do the same thing but in frequency domain. So if you haven't watched my previous videos, do watch it, and my other videos, like I'm doing videos on EMF. I'm solving problems and discussing a little bit about theorems related to EMF. So watch those videos too. So let's get started. So here the source free RLC circuit looks like this. Now we have what we have done is, because this is an LTI system, all the components here are linear components, and they construct a linear time invariant system. That's why superposition principle applies to them. We can also apply KVL, KCL, and this linear system, because this is a linear system, we can apply Laplace transform. So, and because we can apply Laplace transform, we can analyze this system or the circuit in frequency domain quite easily. So we have because L and C are two dynamic elements in this system, we have assumed that a capacitor and inductor has initial voltage and current respectively, and so the corresponding linear transformation in the Laplace domain or frequency domain, the circuit looks like this. uh, Capacitor, resistor, inductor with uh, the sources for the initial values we have assumed. So I have assumed. Now this is also a linear circuit, a linear system, and we can apply KVL, KCL here also. And in time domain, this RLC circuit, um, after applying KVL, generated linear differential equation with constant coefficient, and it was of second order because there are two dynamic elements L and C present in the RLC circuit. Now in the Laplace domain or in frequency domain, this circuit, the system will generate algebraic equation, not a differential equation. Okay, so it becomes more easy to analyze the circuit or solve the equation, because it becomes an algebraic equation. So let us apply KVL. So in frequency domain analysis by KVL applied here. So loop current is, for loop current is, so R I is plus 1 by SC is plus SL I is, and the two sources, which is VO by S, and there is no external source. Okay, so for this there is no external source like 0. So so now if we just rearrange this, so R plus 1 by SC plus SL is, which is the loop current, the current through all the components in Laplace domain, and the initial current voltages. So now if we take L by S out, so L by S out, so it will give us S square plus R by L S plus 1 by LC VO S plus LIO. Now it's starting to get to a more standardized form, you can see here. So if I take the L by S to right half side, so it will give us, so R by LS plus 1 by LC IS, and L by S is VO by L plus SIO. Now we just have to find IS, the current. So VO by L S square plus R by L S plus 1 by LC plus SIO by S square plus R by L S plus 1 by LC. Now what we're gonna do is we're gonna factorize the second order term. So the second order term we found is, or I found, so S square plus R by L S plus 1 by LC. So we want to factor this so that it looks like 1 by, say, S minus lambda 1 S minus lambda 2. So we're gonna uh, make this second order term look like this. So here it is S square minus lambda 1 plus lambda 2 S plus lambda 1 lambda 2. So if we just equate the coefficients here, so it will give us, so lambda 1 plus lambda 2 is equals to, so this coefficient equals to R by L, and we take the minus to R by L, so minus R by L, and lambda 1 cross lambda 2 here, which equals to 1 by LC. Now what we're gonna do is we're gonna apply formula. So lambda 1 minus lambda 2 whole square, we know the lambda 1 plus lambda 2, and we to find the individual lambda 1 and lambda 2, so we're gonna apply this formula. Lambda 1 minus lambda 2 whole square is lambda 1 plus lambda 2 whole square minus 4 lambda 1 lambda 2. Now so lambda 1 plus lambda 2 is minus R by L, so minus R by L whole squared minus 4 lambda 1 lambda 2 is 4 1 by LC, minus 4 1 by LC. Now it will look like, so R squared L squared, and thus lambda 1 minus lambda 2 is root over so R by L whole square. I'm just taking the square out from the individual R and L, so plus, sorry, this is minus, also this is also minus, so minus 4, so minus 4 1 by LC. So we want to take 4 common out, so it will if we take 4 from this 2, so from the root, square root, it will look like this: 2 root over r by 2l whole square minus 1 by LC. If we take um, r by 2l, and we assume, so we assume this as damping factor, so damping factor is zeta, or so in my previous video I uh, wrote zeta like this, so this is not zeta exactly, this is called, so this is basically called psi, and zeta looks like, kind of looks like this. So I kind of like writing this symbol rather than this exact zeta symbol, so I'm gonna use this psi for rest of my um, videos where I'm dealing with damping factors. Say psi is the damping factor r by 2l. So I have defined in my previous circuit analysis videos 1 by LC as natural undamped frequency, which is omega n, so 1 by root LC. So if we just replace these terms by damping factor and omega natural undamped natural frequency, it will look like, so lambda 1 minus lambda 2 is 2, so this is psi square minus omega n squared. If we further define um, omega d as damped natural frequency, which is root over omega n square minus psi square, which is the damping factor square. So if we define damping frequency, damped natural frequency as this, so it will give us lambda 1 minus lambda 2 is 2 j omega d. So we have found lambda 1 minus lambda 2 equals to 2 j omega d, where omega d is natural damped frequency, or damped natural frequency, how you might say. So omega in the natural undamped frequency square minus psi square, which is damping factor. So this is damped natural frequency, and omega n is 1 by root LC, and psi is the damping factor r by 2l, and lambda 1 minus lambda 2 is 2 j omega d. And from this equation we directly found lambda 1 plus lambda 2, which is minus r by l, and as we define damping factor by r by 2l, so it will be minus 2 psi. Now we are gonna do some arithmetic. So if we take the, if we add these two equation or equations, if we add these two equations, plus, so 2 lambda 1 equals 2 common out minus psi plus j omega d, thus lambda 2 is minus psi plus j omega d. And similarly we can get lambda 2, which is minus psi minus this damping factor, and generally it is denoted by zeta. So I like writing psi, so I'm writing this as psi as damping factor, and j omega d. Omega d is damped natural frequency of the RLC circuit. So we have found our two roots. So if you just I have found lambda, sorry, this is lambda 1. So I have found lambda 1 by adding the two equations. You will find lambda 2 by just subtracting. That's it. So these are the two roots. We're just gonna use these two roots in the second term, second order term, and let's see what the uh, current looks like. So these things we have assumed. Now the main equation by which we found by KVL is Is the loop current in the circuit. So VO by, I'm just now I will write the factorized term. So okay, let me write this like the AC square plus 2 psi s plus omega n squared plus SIO by AC square plus 2 psi s plus omega n squared. Now what I'm gonna do is write it in factorized form. So VO by L s minus lambda 1 s minus lambda 2 plus SIO by s minus lambda 1 s minus lambda 2. Now what we're gonna do is we're gonna break this the two terms in partial fractions. So VO by L A by s minus lambda 1 plus B s minus lambda 2 cross, say this is C by s minus lambda 1. So now what we are gonna have to do is we have to find the these terms A, B, C, and D. So to find the arbitrary terms, we are gonna have to equate the coefficients. So we found our partial fractions by breaking this term. So if we just uh, um, multiply s minus lambda 1 cross s minus lambda 2 on both sides, it will give us 1 equals a into s minus lambda 2 plus b into s minus lambda 1. So if we just rearrange this, it will give us a plus b s plus, say, minus, this is, so minus a lambda 2 plus b lambda 1. This now we are gonna equate the coefficients of s and the constant. So a plus equating the coefficients, so equating coefficients, so a plus b equals to 0. So a equals minus b. Now this term, so a lambda 2 plus b lambda 1 equals minus 1. So we are taking the minus to the right hand side of 1. So this, so if we substitute for a, it will give us, so minus b. So uh, b into lambda 1 minus lambda 2 equals minus 1. So b is minus 1 by lambda 1 minus lambda 2. So a will be plus 1 by lambda 1 minus lambda 2. So if we take this term and multiply on both sides, it will give us s equals to c s minus lambda 2 plus d s minus lambda 1. If we just rearrange this, it will give us c plus d s minus c lambda 2 plus d lambda 1. Now equating the coefficients of the variables, so equating of s and constant, so equating coefficient, so c plus d equals s, sorry, 1, c plus d equals 1, and c lambda 2 plus d lambda 1 equals 0. Now from this way we can get c equals minus d lambda 1 by lambda 2. If we just substitute for c here, so mine, which will give us my, say, d common out, so here lambda 2 minus lambda 1 by lambda 2 equals 1, thus d equals lambda 2 by lambda 2 minus lambda 1. We can also write minus lambda 2 by lambda 1 minus lambda 2, and for this we can find c also. C will be minus d, so lambda 1 by plus lambda 1 plus lambda 1 by lambda 1 minus lambda 2. So we have found our arbitrary terms for the partial fractions, which are a is plus 1 by lambda 1 minus lambda 2. So if we just break this, so lambda 1 is minus zeta, so 1 by, so minus psi plus j omega d minus, so minus and minus will be plus, so plus psi plus j omega d, this will be 1 by 2 j omega d. and if we find b, it will be it is minus lambda 1 minus lambda 2, so it is minus 2j omega d. Now also we have found c to be lambda 1 by lambda 1 minus lambda 2, which is plus. So this is lambda 1 by, so lambda 1 minus lambda 2 here is 2j omega d, so j omega d, and d is minus lambda 2 by lambda 1 minus lambda 2, which is minus, I'm for now I am just leaving the lambda 1 in the numerator of the arbitrary constant here, the term arbitrary term here. I'm leaving this b, so b as it is, so 1 by 2 j omega d. We're just gonna substitute these four terms in this equation, and we're gonna apply inverse Laplace transform. So here v, initial voltage across the capacitor by L, so A is plus 1 by 2 j omega d, so 1 by 2 j omega d is minus lambda 1 plus, so it will b is minus 1 by 2 omega g, so omega d, so this is minus 1 by 2 j omega d s minus lambda 2 plus io, the c is lambda 1, so lambda 1 plus lambda 1 by 2 j omega d s minus lambda 1 plus d is minus, so it will be minus here, so minus lambda 2 by 2 j omega d s minus lambda 2. So here in all the terms 2 j omega d is common, so I'm gonna take the common out. So now what we're gonna do is we're gonna apply inverse Laplace transform here. So if we apply inverse Laplace here, so inverse Laplace I is, so inverse Laplace of the current will make the current in time domain, so it, and we are taking the inverse Laplace of this, so 1 by 2 j omega d vo by L exponential lambda 1 t minus exponential lambda 2 t. So this is basic formula for inverse Laplace transform. So here plus io, initial current through the inductor, which is lambda 1 exponential lambda 1 t plus, sorry, minus, this is t, so minus lambda 2 exponential lambda 2 t. Here lambda, so exponential lambda 1 t minus exponential lambda 2 t is, so if we just break the lambda 1 and lambda 2 the roots, so it will give us minus psi plus j omega dt, and minus psi minus lambda 2 is So like this, minus j omega d here t. So if we take the common out, e to the power minus psi, which is the damping factor t, it will leave in the inside the brackets j omega dt plus e to the power minus j omega det. So it will be minus. So here there is minus, not plus. So for the first part it is 1 by omega dl. If we take the g 2j, sorry, if we take 2j 1 by 2j inside this and divide the exponential terms, so here this is vo, initial voltage, and e to the power minus psi t, which is the damping factor. This is like this, and the power j omega dt minus the minus j omega dt by 2j. I'm just rearranging this now, plus io by j omega d. If we just break this lambda here to lambda 1 and lambda 2, the roots, so minus psi plus j omega d t, sorry, j omega d exponential minus psi plus j omega d in the brackets t minus psi minus j omega d cross the exponential minus psi minus j omega d in the brackets t. So this is the uh, complete scenario now. 2 j omega d. So here this is vo by omega dl exponential term. This is the decaying term with the, this is the term with damping factor, and this is sine omega dt plus io by omega d. If we take 2j inside the brackets, it will be like this. So here minus psi, so if we take minus psi and minus psi with exponential term is, so here is also a minus psi, here is also minus psi, so minus psi taking common and exponential j omega dt minus e to the power minus j omega dt by 2j and plus omega d. So if we take omega d common, it will be like this. So exponential j omega dt plus exponential minus j omega dt by 2. So here j and this j will cut out, so there will be no j. So this, and we have extra exponential term. Okay, I'm gonna write this here. So plus I initial current omega d, this exponential, we have taken the this exponential term out of the bracket. So this is the exponential damping factor only. So now this is become um, seemingly understandable form of the solution. So this part is sine omega dt and this part is cos omega dt. So what is left now is, so this leaves us with the result. After inverse Laplace transform, we found, say, let me write this here, room. So it, the current response for the series RLC circuit. So VO by omega dl exponential, this is the damping coefficient, the exponential term with the damping coefficient or damping factor, sine omega dt plus io by omega d exponential term with damping factor again in the brackets minus psi, which is the damping factor itself, sine omega dt plus omega d cos omega dt. So here this term. So if I write this cleanly in single line, so in frequency domain analysis, the response of the source free series RC circuit is the current, loop current through all the elements, which is it, which is equals to exponential term V or initial voltage across the capacitor, omega d damped natural frequency inductance, sine omega dt plus initial current through the inductor cos omega dt minus damping factor psi or zeta, I am writing psi here, by damped natural frequency of the RLC circuit, sine omega dt bracket closed. This is the full answer. So in my time domain analysis video, this term had minus in it, extra minus. So I don't know if I have made any mistakes in this derivation in the frequency domain analysis. I think mostly I have done all the things right, so you can check it yourself and see that if I have made any mistakes or not. If I have made any mistakes, you can tell me. And that's it for this video. uh, so in this video I have derived the circuit response of the series source free RLC circuit, and that's it. Thank you for watching this far. I hope you understood my calculations and explanations, and thank you for watching.